All right, I'd like to welcome Nav and Vijay, come to talk about I/O latency, predictable I/O latency.
Okay. Thank you, everybody, for your participation, especially on a Friday afternoon. I'm Navneeth Kankani from the Facebook infrastructure team, and my friend Vijayan, software engineer from Facebook. This talk is going to be a call to action for a hardware-software co-design approach for solving this problem of predictable I/O latency. By the end of this talk, we hope to be able to articulate the problem, surface some of the trade-offs that exist, and provide a RocksDB use case that leverages the flexible OCP hardware that we have to build a better together solution. So just to build up some context, this is the landscape of today's storage types, right from transactional SRAM storage all the way till tape media archival storage. We can classify this in various ways based on capacity, read-write latencies, different types of access types, block, file, object, and different storage applications as well. When we talk about hardware-software co-design approach, it is important to factor in the applications for which this storage hardware is being used. For the rest of the talk, we're going to use storage class memory and NAND flash as a proxy for our storage hardware to further our discussion. So before we delve into the problem statement, let's look at what are the challenges we are facing. Density across all different storage media types is increasing. NAND flash densities are doubling every 18 months. However, the bandwidth and IOPS is not increasing at the same rate. And hence, bandwidth per terabyte and IOPS per terabyte is decreasing. Along with that, we see that the number of NAND dies in an SSD is dropping. And what this implies is the number of read and write collisions is increasing. It not only increases the overall latency, but the unpredictability is also increasing. This, along with the future NAND optimizations and the 3D NAND layer scaling that is going on, adds to that unpredictability. So let's see how this storage latency matters. And to go about that, let's touch upon the hyperscale architecture briefly. So if a user requests a friend's photograph or a news feed, that user request goes through massive amounts of sharding across many web servers at various data center locations that we have. And after going through a caching layer, it incurs a huge fan out at our backend and results into a query in one of our many databases that we have. All of these servers and data centers are connected through a sophisticated network topology, and the data has to be stitched from multiple servers to be presented for a news feed or a friend's photograph. So because of the massive level of sharding that we have, we observe asymmetricity and read and write access patterns. The picture on the left shows the asymmetricity across shards for a particular server. As you can see, the read QPS is all the way varying from 10 to 800. Also, the picture on the right shows the read bandwidth variation at different latency levels, all the way from 200 megabytes to 40 megabytes. And that's a 5x variation that we are seeing. And this is for a particular storage space. So we have seen the unpredictability and asymmetricity that exists. Let's connect it back to the service level SLA now. Let's take an example of a server that responds within 1 millisecond, but with a P99 latency of 1 second. When a user data has to be stitched from 100 such servers in parallel, it results into a 60% chance that a user request will see a latency of more than 1 second. Even if we were to drop that frequency to 1 in 10,000, let's say 4.9 latency, and with a scale of number of IOs per user request going to 2,000, we still see a 20% probability that the user request is going to see higher latencies, like 1 second. This is the unpredictable latency compounding problem at the service level. And these SLAs are totally not acceptable by many of the hyperscale applications. So to summarize the problem definition, we do have unpredictable latency in the storage stack today, and this problem is only getting worse with the technology scaling. And for a large-scale distributed system, there is a need for predictable latency in spite of all the unpredictable components that exist. And with the scale at which the Facebook infrastructure is growing, the need for such a problem to be solved is ever increasing. Let's look at some of the solutions that exist. Some of the presenters have touched upon some of the solutions in detail. So since we are taking NAND and SCM as proxy, we're going to talk about solutions at the hardware layer which are relevant to NAND. So NAND has multiple planes, and allowing for parallel operations across these planes increases the IOPS and reduces the read and write collisions, which helps with latency. We can have preferential scheduling at the network layer, at the NVMe controller, or the background activity scheduling to help with the latency as well. We have device features like write and erase suspends, where a write can be hold and to allow for the read operations to go ahead. We have isolation schemes like streams. Some of the presenters touched upon it in more detail. We have NVMe sets, which are really the latency isolated regions. Set 0 can have the write going on, whereas set 1 and 2 may have the reads going on, so that the reads and writes are not impacted by each other. We have predictable latency modes, where we have deterministic windows, where a user request can go ahead, and non-deterministic windows are reserved for all the background activities. We do have maximum thresholds that we can set for read recovery limits. For example, all the heroic read recovery that needs to happen can be aborted, and the read can be fetched from a replica in one of our data centers. So again, those were some examples at the hardware layer. Let's look at what happens, what can we do at the software layer to solve this problem. Shard management and rebalancing with respect to load, capacity, or health happens all the time, but we can go one step further and make the shard management and rebalancing aware of the underlying storage hardware to optimize for latency. We have pooling and striping, where volume groups can be created and logical volumes are carved out of the physical SSDs that we have, such that the IOs is spread across the SSDs and helps us operate in a lower response time region. We can have storage class memory and use tiering of block and page caches between DRAM and SCMs. The picture on the bottom, you can see the flash IOPS are dramatically dropped if you use a high DRAM solution or a tiered solution which uses storage class memories like Intel Optane and low latency NANDs like ZNAND. Write coalescing is a technique where we sequentialize the random writes using some NVRAM buffers. We could do dynamic resizing of these logical volumes as we see fit to optimize for latency. So these local optimizations at hardware and software layer exist, and I only alluded to some of the examples. But those examples, those solutions don't come for free. We pay with these trade-offs to pay for this, to buy those latency credits. One of the things is machines are shared across multiple applications for processor caches, network and memory bandwidth, and sometimes we have to restrict these resource sharing to guarantee certain SLAs. The picture here shows the response time exponentially increasing with the number of IOPS. What this means is it limits our scaling of the workloads. For example, a database instance on a server has to be limited because of this response time. We may have to operate in the lower queue depth regions across multiple levels of servers. We may have to throttle the write rates. And the power management may not be as efficient as possible because we are trying to buy some of these credits. So because these latency solutions come with these trade-offs, there is a need for a concurrent optimization at the system level, which includes hardware and software, to solve for the predictable latency problem. And we have seen clearly that if you optimize only at the hardware layer, the local optimizations are not going to be enough, especially because of the technology scaling is not giving us the same latency improvements that we are used to in the past. And we need to leverage some of these trade-offs at the software and hardware layer together and feed into the future designs as well. And last but not the least, the knowledge of applications for which this storage hardware is being used for opens up new opportunities and windows of opportunities for changing our architectures. So with that, I'm going to touch upon some of the building blocks of OCP hardware, which we are going to use to demonstrate a use case for a RocksDB. Yosemite is our second generation chassis that houses 4 Twin Lakes, which is the single socket servers based on Skylake DE CPU. Tioga Pass is a dual socket server based on Skylake SP CPU. And these servers can have different form factors of flash, like M.2 cards. Ava is an adapter card that can house 4 M.2 SSDs and can go in one of these servers. Lightning JBOF houses massive amounts of flash that we use for our disaggregated solution today. So from here on, my friend Vijayan is going to use these flexible OCP hardware components to show a co-design approach for a RocksDB use case.
Thanks, Navneeth. So Navneeth pointed out that for hyperscale solutions, it is critical to pay attention to latency. Pointed out that there is a lot of sharding going on in these architectures, and that requests at the highest level, they translate into multiple requests at the lowest levels, that many IOs have to be issued, the results of these gathered and presented back to the user. So what do we do when that's the top level requirement? There is a lot we can do to bound the tail latency. There is also work we can do towards reducing the latency overall. So if we have low latency operations, then we have more headroom, and we will hit the bad cases less often. So here are two possible architectures. One of the architectures that has been historically used is to have servers with locally attached flash, which is very nice for latency, but it's not so good for sharing. It's not so good for capacity utilization, because there is often stranded storage on the left side, in the solution on the left side. In response to this, people have built disaggregated solutions in which we use a platform like Lightning and place all the SSDs inside of that. These servers access these SSDs over the network. So let's take a look at the application stack that runs on either the local storage or networked remote storage. What it typically looks like is a stack in which I have listed just a few of the components. There are drivers at the lowest level. There is a file system on top. And many of the databases we use are structured on top of RocksDB. And on top of RocksDB, there is typically an higher level database like MySQL or ZPDB. These services are sharded very widely. That's something we should always keep in mind. There are a couple of different architectural options that we've looked at. The one on the left says that we are using a platform like Lightning, and RocksDB is running on each of the servers within the rack, and it is communicating with one of the Lightning devices within the rack as well, and exchanging block IOs. Servers are able to drive block IOs to a fairly high bandwidth, typically a few gigabytes. There is another split that is possible, and it's something where the networking bandwidth requirement goes down dramatically. And for the cost of about 100 or thereabouts megabyte per second exchange of keys and values, we're able to push the ROCks implementation down into the storage layer onto the platform which houses the SSDs, so that most of the high bandwidth communication happens on local PCI Express. So no longer communicating via the top of rack switch. So the point there is that we pay attention to the locality of communication that is needed. Where is bandwidth particularly high, and where else can we choose a point in the application stack where the bandwidth is much lower. So this is a problem that occurs in most key value stores. RocksDB is one of the more efficient ones and is heavily optimized for lower I/O and lower random I/O. So it's a pretty good implementation, but the problem is sort of endemic to key value stores, occurs everywhere. So this This is a kind of problem that it is necessary to devise general solutions for. And the problem of read and write amplification deserves like a solution that has more or less locality in it. So this is the example solution that we presented, like could be put together fairly easily. One of the reasons this was possible is because there is plenty of choice within the OCP ecosystem and multiple different solutions. Lightning is one of the solutions which has worked well, but Yosemite is an alternative solution, not designed necessarily for storage, but can be used as a storage platform. This is made possible because it has boards which host M.2 cards, and so with the increasing density of M.2 cards, it is possible for us to structure what looks like a storage solution or what looks like a joint combined compute and storage solution in which multiple different bits of software are distributed in desirable ways. So the core ask is for flexible architectures in which we can dynamically alter the ratios of how much CPU horsepower we have, how much DRAM capacity we have, and how much SSD we are able to address. So we want to be able to take a look at the application, want to be able to pick the best ratios for it, and be able to structure that in choice of components for our racks. So that's basically the quick summary. So we started with Lightning-based solutions. We're able to transfer the knowledge we gained onto Yosemite, and we're able to get better efficiencies. That's made possible because there were choices. Without choices, we would have constrained solutions. So in summary, like OCP solutions should permit ratios which are more flexible. So that's getting efficiency at scale is very hard. The problem is challenging, and at scale, the same kind of solution applied to hundreds of shards which have different utilization at different times needs for flexible designs to be put together, which are somewhat dynamic, but give us different ratios to work with.
So then in summary, we would like to leave you with 3 points. The first one is we strongly believe that this problem of predictable I/O latency is amenable to a hardware-software co-design approach, and by working together towards a holistic solution, we will be better together. The next one is what Vijayan pointed out, to use the flexibility that the OCP hardware provides to build multiple balanced solutions, whether it's for efficiency or for good latency or for resource sharing. And then last but not the least is, please don't work in isolation. Let's look at customizing the storage architectures for the applications where they're going to be used. And with that, we'd like to thank you for listening and for your time, especially on a Friday afternoon. And we only were able to allude to certain OCP hardware pieces, so please visit the booth for more information on the OCP hardware. Thank you very much.
Thank you.
Okay, with time for a quick question, too.
In Facebook, do you guys use like open channel SSDs? Do you customize SSDs with some vendors? Thanks.
So at Facebook, we are very open to ideas. We are always open to exploring ideas with all the vendors and suppliers. So definitely, we can chat offline about how we can work together.
Do you have an example slide of actual latency numbers that you have recorded?
Next opportunity, we'll present the numbers.
You Oh, can you go back to the partition of the storage network, the first few slides? Yeah. Okay. So, does in the last slide you say the RocksDB is the RocksDB run inside the storage node? Yeah.
Is this the one?
The RocksDB.
Yes.
Okay, will be running in the storage server, right?
That's
Instead of the host server.
That's the basic idea. And
Okay,
this is the reason like we need more CPU horsepower and DRAM in the storage node than Lightning has. Yeah.
All right, we have to go to Jason's talk now. So thank you very much.
Thank you.
Thanks.